Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, everybody. It's my pleasure to introduce Jim Ray. Jim and I actually know each other for close to 20 years now, isn't it?
Something like that.
Oh, yeah, well, it's a long time. Anyway, Jim is a professor at the School of Interactive Computing at Georgia Tech. Jim graduated from CMU back in '95, and he was with DEC/Compaq before he joined Georgia Tech. So Jim has done a lot of very interesting work applying machine learning techniques to problems in computer vision and robotics. Jim?
Thanks, Sangmin. Well, it's great to be here. I'm going to be talking today about some work that we're doing in my group. And this is work with some of my students, mostly the first student here, Karthir Prabhakar, and also my collaborator, Gregory Abowd. So just to give you some pictures of those folks. So today I'll be talking about sort of two topics. So one topic is a new technique for video analysis we've developed recently. And I'm also going to provide some motivation for this work in terms of looking at children's behavior for the study of behavioral disorders like autism. So there's sort of two themes in my talk that I'll be going over. So I want to start by showing you a video clip. Just take a look at this for a second or two. So I like this clip for a number of reasons. The first is that my son is in it. He's very cute, I'm sure you'll agree. The temptation to use your kids in these things is just impossible to resist. But another nice thing about this video clip is it shows a lot of very interesting behavior. So if you look at what my son is doing, if you look at the interaction we're having, if you look at all manner of his facial expressions, postures, and so on, there's a very rich sort of expression that's taking place, unfolding over time as this video plays. And one of the motivations for this work is the desire to understand these kinds of behavioral interactions and understand them in a very fine-grained way. So the most basic thing would be to say, well, this is an interaction between two people, and then you could go a little further and say, in fact, these people are playing a social game, they're kicking the ball back and forth. And then you could go even deeper and look at particular moments in time and ask, how is the child feeling? Maybe what is their expression? What can you deduce about even their emotional state? And drill down. So this kind of content of children and interactions of this nature has a lot of rich detail. And one of the things that I want to talk about today is how we can use computer vision techniques to begin to drill down into this kind of footage and really extract some of the relevant behaviors and relevant parameters of behaviors that we can find there. So you can think of a number of goals: find behaviors of interest, categorize different kinds of interactions together, and then quantify, even if we go far enough, various characteristics of behavior, specific details of behavior. Now, the most basic question that arises in a situation like this is, how should we represent this video? How should we build representations that support the analysis of behavior? And this has been studied in vision for a long time in areas like activity recognition, for example. But really, it's only in recent years, I would say, that we've really had the ability to get traction with fairly realistic and complicated footage. So we've seen in the last 5 years examples of looking at movie footage and finding actions in movies, looking at web videos and categorizing them in various ways. And of course, the great thing about this is that it lets us move away from the kind of little bit fake content we used in the past and really look at realistic videos in the real world. You may have seen this video in the wild as a characterization. But yet, in spite of that work, I would say there's still a lot of work that needs to be done in really thinking about representations of video that have the right properties for the kinds of analysis I'll be talking about. And I'm going to essentially present to you today a new representation that I think has some interesting benefits. So, the problem we always face is how to visualize what's going on in the video over time and understand the temporal evolution. And this is a standard visualization I'm sure you've all seen of taking the video volume and slicing it at a particular scan line. And I want to just draw your attention to some details of the structure of this particular slice. You can see these sort of undulating patterns running in the time axis here. And of course, this little pattern here is my son's leg, essentially, as he plays ball with me. And this little pattern here is my arm as I catch the ball and roll it back to him. And this is sort of actually it's the sock of this person in the background here that's kind of moving around. So if you look at this in the temporal dimension, you can see a variety of structure. And in fact, you can even see how there's a kind of back and forth, as you saw in the video, captured in time in this pattern of undulation, if you will, of my arm and his leg. So the question is, how could we get a handle on this kind of temporal structure? How could we extract it and represent it? Okay, and so there are some standard ways of doing that. Yes, Singmin.
Yeah, Jim, are you assuming that the camera is always stationary in this case?
So you'll see the footage in a second that we're working with, and in that footage, the camera is not ever perfectly stationary, so it's not on a tripod, for example. We're really trying to work with the kind of footage you'd get from home movies. So a videographer that's not a professional that's just going to hold the camera and walk around. Now, we're not going to assume that you're going to be Spielberg and kind of doing, complete circular panning shots around the action of interest. So there's assumption that there's a kind of standard viewpoint, if you will, into the action that lets you see what's going on. And then there may be, there will be actually camera shake and slight camera movements as people, modify their angle and their hand moves and so on. So it's not going to be an assumption about static camera, but it's not going to be, as I said, aggressive sort of panning shots either. Okay, so the standard way to handle this that we've seen is this use of visual words. So this is a very popular representation these days where you essentially apply a little interest point to the video volume that looks for regions where something is changing, there's a strong motion, there's a strong texture gradient of some kind. And then you cluster these regions, you build a descriptor for these regions that you can identify and then cluster them. And you get this kind of representation where the green points are all visual words in the same cluster, the purple points and blue points likewise. And this does a pretty good job of actually capturing at least the kind of the 0th order places where things are happening. So you can see that there's a good number of these points on my arm, a good number on my son's leg, and so on. But there's nothing in this pattern that you could look at that would really expose what's really happening there. It's just a bunch of points that characterize the volume. It's a dictionary characterization of the volume. And the way we've been able to make progress in vision and working with this and being able to categorize video, for example, is by taking all these points and just throwing them into a big SVM. So you put a histogram window. Usually the simplest thing is just a huge window that covers the entire volume. Just histogram all the points. And then let the SVM see many examples of a behavior you care about and lots of behaviors you don't care about. And the SVM can figure out in this feature space which of these points and which combinations are really discriminative and useful and which ones are not. Okay? And this proposal that I described has been used in many papers in the last 5 years, including some fairly impressive things with working with Hollywood movies and so on. But it has a big problem, and the biggest problem is that it's supervised. And this means that in order to use this, you've got to have lots of examples of what you want and lots of examples of what you don't want, which means you need to know in advance what you're looking for, which when you think about behavior can be somewhat problematic. Often we want to know interesting things that are going on in videos without knowing exactly what it is that we're interested in finding, and without wanting to actually go in and make a huge investment in collecting training data and building classifiers before we know what's really important. So there's a real need in this area for representations and tools that don't require supervision, but still have the ability to extract some kind of useful structure of the underlying evolving pattern. And so I'll be talking today about a new technique that does this. And so the technique that I'm going to show you can produce a representation like this. And this is essentially a reclustering or a reorganization of these points that exposes the groups of points that are interacting and the groups that are not. And so it puts my arm and my son's leg into one cluster, this cyan cluster here, because it can recognize that there's an interaction taking place between the two of us. And it can successfully discriminate, for example, these sets of points in yellow here that are in the field of view of the camera, moving in many cases and spatially intermixed with these points, and yet not participating in our interaction at all, because these points are actually part of the background of the scene. Okay, so that's the top level bit of the talk, is how to generate a representation like the one on the right, given a set of visual words on the left. Okay, so I'm going to now just kind of give you the overview. So we're going to look at a particular methodology for doing this organization, which comes from the study of temporal causality. And then I'm going to show you some of the applications of this to looking at social games. And then if there's time, I'll talk about some categorization work that's a little more recent that we've just done. And of course, feel free to jump in anytime. Okay. All right, so the starting point for this work for us was really trying to think about if we could devise some tools that would work in giving us the temporal structure. I feel that although there's been a lot of work on video and computer vision, I would argue that most of that work has not really considered the temporal structure of the video to any great degree. So we tend to approach video by applying the tools we're familiar with from working with image collections, a lot of geometric analysis, a lot of registration, a lot of even tracking, but it's really doing kind of spatial analysis over time. So time is just kind of an indexing variable to essentially a spatial process. And so I think there's really a lot of need in vision today for techniques that can treat time in kind of a first-class variable that should be studied on its own, not just as an index to other things. So this idea, of course, is very central to the study of time series data, where it's really this collection over time is all that matters. And there's a very nice piece of early work in the 60s on looking at a very basic problem of causal analysis in time series data. So this is the problem. You've got two signals, x and y. What you want to know is whether there's evidence for y having an influence on x. So think about these as a stock price. Suppose x is the stock price of a company, and y is, for example, the price of a raw material that's used to make that company's products. So you can imagine if the raw material price fluctuates, that might have some bearing on the price of the company, and that stock might fluctuate later in some way. So Clive Granger studied this problem using sort of the basic techniques of time series modeling, and he came up with a very nice result that he got the Nobel Prize for in the 60s. And so Granger's idea was the following. Suppose we consider two experiments, two models, if you will, for this data. And they're going to be based on making predictions about future values of x given past values of these signals. So this is a forecasting problem. Given some data from the past, make predictions about the future, and use the error or the quality of those predictions to make assertions about the quality of different models. So for example, we could look at x, the signal x on its own, and make predictions about x. So that's an example of how you would do that. So you'd have an AR model here, an autoregressive model, take the past values of x and use those values to predict the next sample, the next measurement of x. And you get this predicted curve here in red. This is the predicted value of x given its past values alone. And then you can compare that to predictions that are made with x and y together. So now I take x and y, I build a joint model, AR model out of both of them, and I repeat the prediction process using the joint predictor for these two signals. And Granger's argument was that if this predictor on the bottom here that puts x and y together, if that predictor has lower error than the predictor that's based on x alone, then that's evidence for y being causally related to x. Because after all, if y had no influence on x, how could knowledge of the past values of y give you an improvement in your ability to predict x's values over time? Yes, Rick?
What are U and V in this case?
So these are noise processes. So in this modeling paradigm, there's a linear part of your model which is just literally taking the past values and weighting them and then adding them up to give you the future value. And then there's a noise term which tells you how accurate this prediction is. And so that noise is going to be stationary, and over time there's some variance that you'll experience in your prediction, and that variance is a measure of the error. So if you think about subtracting this term here from this term, the residual is actually, that difference is actually the error, how much error there is in your prediction, and U is a stochastic variable that captures that error. And so the test, in fact, looks simply at the variance, the covariance of U and V, the two noise models, and it measures which one of them is smaller, essentially, to decide whether there's evidence for this causal test. Well, it's done over a long interval of time, though, so over a whole set of data. So the nice thing about this, so there's several nice things about this. So, causality is obviously a loaded thing. And so, in the 60s, I think there was sort of less, there may have been less concern about causality than there is today with all the graphical models work, for example, in causal analysis. So you've got to take the causal part of this with a grain of salt. This is really a very specific data-driven testing paradigm for looking at whether signals interact or not. But the nice thing about this is that it is data-driven, which means you don't need any kind of process model of the world to test whether one thing is related to another. So there's been other work in vision that looks at effect and at cause, for example, work in looking at models of naive physics to decide whether objects can make contact or collide or what have you. And those models are very interesting, but they need some notion of physics, some notion of what's happening in the world. The nice thing about this is it doesn't require any sort of domain models. It's just literally looking at the signals and making some analysis. However, although this is a technique that's been around for a long time, it really hasn't been used very much in vision. And the reason is that this is really not a very good paradigm in and of itself for doing things with images. And there's a couple of reasons for this. But the main one, I think, is that this requires you to have time series data, which means regularly sampled measurements of things that matter to you in the scene. And that's very hard to get in vision. That essentially means a tracking problem. And tracking problems are really hard to solve for non-trivial footage over long periods of time. But even more than that, I think it's often the case that in vision, the kind of relationships of interest to us don't really exist at the frame level, at the sample level. Think about following somebody. So it's not that you're going to be maintaining a fixed distance to that person at all times. It's really about events. I'm going to follow this person, and they're going to turn left, and then at some point I'm going to turn left, and then they're going to cross the street, and then I'm going to cross the street. And so it's really these discrete moments where a decision is made or a change is made, and at that moment you see whether or not two actors are in fact synchronized in some way. Okay, and if you think about, again, the children's video I showed you earlier, there's moments in which I'm responding to my son, but I'm not responding at every second, every millisecond to what he's doing, right? So I think to really make this kind of causal analysis effective in vision, it has to be reframed not in terms of continuous time measurements as a time series, but rather in terms of event data. And in particular, we'd like to leverage the use of visual words, which in terms of video is a kind of event as well, to really make this be powerful. And so really the point at which we were able to get some results here was really in coming up with a way to kind of map this machinery into an event-based formulation. Okay, so the starting point is to think of visual words, and I want to try to persuade you to think of them in a little bit of a different light than you may have before. So I just want to play you a little simple video clip here of some of my students kind of acting silly. And what you're seeing here are the visual words that are detected. This is the standard Laptev space-time interest point operator going on here, and just showing you what these words look like over time. Okay, so I want you to kind of focus on these words, and what I'm going to persuade you is that there's really three things that are going on here with each of these visual words. So there's the frames in which they occur, so they're either on the screen or they're not, and those are the frame times in which they occur. Then there's the spatial positions at which they occur, where are they in the image. And then there's actually a question of how many words you have at any one time, because there's a multi-scale thing, and so you get multiple responses at a given point in time to this operator. And what I'm going to argue is that actually of all those three things, the only thing that really matters is the time of occurrence. Okay, so if you think about it, if you translate the camera, pan the camera a little bit as these guys are doing this, then the positions of all those words are going to change, at least in pixel coordinates, but it's not going to affect the interaction that's going on at all. And furthermore, having multiple responses at a given scale, at a given point, may tell you something about the scale of the motion that's happening, but it's pretty random and not really something that has a lot of informative aspects as far as I can tell. So the key thing about these words is simply when they occur. So you could think about then, from that point of view, looking at each word sort of one by one. So looking at the yellow one, for example, and just taking notice of when it occurs. So it occurs at a certain frame, then at another frame, then another frame. And you can basically just keep track of these occurrences in time. So you're just marking when in time each of these visual words occurs. Okay? And so then you can do that for other visual words as well. You can look at the blue one, for example, and make a similar representation. And so what you can do then is map the set of visual words over here on the left that occur in the video to a set of times of occurrence on the right. And this has a mathematical representation as a statistical process. It's known as a point process. So a point process is a stochastic process where the only thing that matters essentially are the times at which events occur. No other information about those events is relevant to the description. Okay, so the key to this talk is that we're going to make this observation that a collection of space-time visual words is really a multiple point process. And that point process then can be studied in terms of its dynamics. So we can look at the interleaving, for example, of these events in time. And you can notice, even in this simple example, some very rich structure that's here. You can see, for example, that the green and the blue processes seem to be related closely in some way. The red process seems like it's also perhaps influenced by them. And the yellow process here is clearly marching to the beat of a different drummer. It doesn't seem to be driven in any sense by the processes from above. And of course, all that makes sense if you go back and think about the video and how these points are being produced, that this is actually the case. And so the main point of this talk is going to be a procedure for taking this kind of data and actually identifying which of these processes are interacting and which ones are not, and using that to then group these data in a new way. Okay, so let's see how that works. So the key to making this work out is to move away from this time series domain, excuse me, where you need regularly sampled data. And it turns out this was done actually in the 80s by some folks that looked at formulating the classical Granger causality in the frequency domain, so in the spectral domain. And so the idea is actually very straightforward. It's a transfer function view of the same problem. So it's the same problem from before. X and Y are two signals. We want to know whether there's evidence for Y influencing X. And rather than thinking about this in terms of fitting AR models and then modeling the data directly at that level, what you instead think about is in terms of transfer functions. So there's two signals. They're driven by their noise processes over here. And we're looking at the influence of this noise process driving X directly, which is the first sort of path, the sort of individual path for X. And then we want to compare that to the effect of this noise process for Y also driving X via the interaction between X and Y. And so just like we looked at the process, the comparison between two predictors from before in the time domain, excuse me, now we can look at the same effect, essentially, in terms of these two processes in the spectral domain. So you can take the spectral behavior of X as a signal, and you can decompose it into two pieces, the part that's intrinsic to X itself, which is this direct path, and then the part that comes through Y, which is this indirect path that I was alluding to. And you can simply compare the magnitude of these two paths, these two components, if you will, in explaining the overall power in X, and that's another way to formulate this same causal test. And it's numerically, if you have a large amount of time series data, and then you do either way, mathematically it's the same. But this has a huge advantage that the spectral domain testing can be done for point processes as well. So there are some standard techniques in the literature for estimating spectral matrices for point processes, and we can use that directly with this test to analyze our data. So this is the way the test works out. You take these two pieces that I alluded to, and you form a new test here, which is based on the spectral matrices. And this construction can now be done entirely numerically from our point process data. So we can take the point process data, we can estimate the spectral matrix, and then we can factorize it to obtain the elements that are needed in this expression. And this is all sort of standard signal processing stuff that's been done for decades. So it's pretty robust, and there's actually quite good code available in MATLAB to do this. Okay. So let me now take you through this process. So you start with your data, as I mentioned. You first form the spectral matrix that essentially shows how much energy there is in different interactions among these variables. And at this point, it's a symmetric process. It's just the interaction, bilateral interaction between these signals. And then you form from that the causal function that I showed you earlier, and this generates an asymmetric matrix where you're now normalizing these symmetric relations by the individual powers of each of the signals. And so you get this nice matrix here that shows you, for all pairs of possible processes in my representation, what's the likelihood or what's the energy for there being some kind of causal relationship. And of course, what you can see is that there's always some energy everywhere, so none of these are zero. So then you need some kind of statistical test to really decide whether there's strength for an interaction between two processes or not. And that's really one of Granger's contributions early on, was to formulate a nice statistical testing framework for looking at a principled way to make decisions about whether there's influence or there isn't. And we can do the same thing in the spectral domain as well. So the way this works as a process is you just integrate, these are all signals where frequency is along the axis here. This is the frequency axis, and this is the energy axis. And you just integrate this signal and frequency, just add it up essentially, and that gives you a single score. And then there's a procedure for doing hypothesis testing that lets you say at a certain confidence level what threshold you need to make a threshold decision about this matrix. And so you threshold this matrix with respect to your threshold that comes from your hypothesis testing framework at a desired confidence level, and that gives you a final matrix here which shows the strength of causal interaction between processes, with zeros occurring everywhere there's a below threshold interaction. So these zeros then mean lack of interaction between two processes, and these numbers indicate evidence for an interaction at varying strengths. And so this is now the new representation of this set of visual words that really exposes in a direct way their sort of pairwise relations over time. And we can use this to organize the data in a new way.
So Jim, when you say for G and G, all the diagonal elements are zero.
Right.
Does that mean that you can't use itself to predict the future?
What it means is that this variable's influence on itself is already handled by this formula. If you go back to the formula I showed you earlier, this quantity here is the total power of the signal of the signal's variability. It incorporates the signal's ability to influence itself, which is this term here, and so that's going to be essentially taken care of by my model already. So I don't need to do anything special about that. So the point of this matrix is to show the ones that are not covered by the signal itself. It's the cross terms. So this is flat essentially because we're not studying the autocovariance here for the signal. We're studying, in fact, this feedback channel from the other signal. So it's by construction that it looks like that. Excuse me. Okay, so once you have this, then the question is how to interpret this data. And so the most basic thing you can do is to interpret this as the adjacency matrix for a graph. And if you do that, you get something that looks like this. And so this graph, which we call the causal graph, is a way of showing, in terms of these pairwise relationships, what the actual sort of overall structure of these points are. So you've got a set of points that are related through some causal interactions, and there's a complex structure here depending upon which of these entries are 0 and so on. But the key point about this really is that there's this extra piece, this subgraph, if you will, that's disjoint from the other pieces. That doesn't have any connections. And so often you'll find when there are multiple processes in the video that are interacting at different rates, you'll have this effect that several of them will sort of fall out as their own independent subgraph, leaving the other pieces behind. And this is really the goal of this analysis, to expose these pieces that are interacting and segregate away the pieces that are not part of the story. And so you can see that here in a more complicated example. I'll just play you another one here just so you can get the idea. So this is sort of another example of this toy problem. And again, if you do the analysis, what you get is on the left, you get one large graph, which is produced by this guy's jumping around all these visual words, all with very complex interactions. And then you get a very simple graph over here for the little set of visual words for these guys. And again, the point is these graphs are disjoint. So we can now think about taking a set of visual words and doing this analysis that I described, which is very, very easy to do and actually very fast as well. And you can then use that to partition the data into multiple sets that are disjoint in the manner that I've been describing. So this is essentially a new way to do segmentation of video. Segmentation not based on the normal kind of appearance properties, color and motion and things like that, but actually based on the longer-term temporal structure of the data, which points seem to be interacting with other points in producing the final output. Okay, so that's the key technical piece, and now I just want to show you some results, basically, of how it works out. Yes?
So didn't you investigate the possibility that the two events that happening interact together?
Right.
Like after a certain amount of frames.
That's right.
This guy will play with them.
That's right. That's right.
So how will the algorithm handle such thing? Because you will have low confidence at the beginning that there is no interaction, and then high confidence.
Right. That's right. So there's essentially a basic assumption here that this is a stationary system, so that the statistics that govern the interaction of these point processes are not themselves changing over time. Now, of course, in reality, they will be. And the way we handle that in practice is by having a sliding window. So we set a window in time of a certain size, and that window size is chosen to be big enough to capture enough samples to show whether something is present or not. And then we slide that window along. And so what we would find then in the example you gave is that in the beginning where there's no interaction, we'd get no evidence for an interaction. And then at the end, when they start doing things together, we would hopefully detect that. So that's kind of the simplest approximation to handling a kind of non-stationary process, which things in video are truly non-stationary in reality. Yes?
So this guy was jumping around and sort of moving behind the other two. Mm-hmm. That occlusion could look like interaction.
That's right, it could. In fact, pardon me, go ahead.
Is that something that you want to come out?
Right. So the way to think about this, I think, is really in the spirit of all segmentation algorithms, which is that it's a way to organize your data. It's unlikely to produce the truth, for all situations that you care about. So, I don't expect this to, and I'll show you many examples in this talk, and you'll see that there are cases where it will make mistakes. It'll do things that are not semantically the right grouping, just like every other segmentation algorithm in Vision makes similar kinds of mistakes. So really our goal here is to describe a new tool that can be used to examine the data. So you could, for example, change your confidence level in your threshold test and then get different graphs to reflect different degrees of causal interaction within this data. And that becomes a tool for kind of exploring the interaction space in this video in a way that lets you just turn a parameter and see how things fall out. So that's really the spirit of it, I think, is not that I expect this to produce the right answer at all times, because in the end it's still very noisy, sparse features. They don't really capture what's going on in video, in any really, they're not the truth in some sense, right? So it would be strange if they actually worked, perfectly in all times. But you're right. I mean, things like, processes that are spatially juxtaposed, especially if the background process fires a lot, then it's always interacting. There's always some event, and there's another event in this background process. It's very likely it's going to get mixed up. Okay, now if it fires more sparsely, you may still be able to segregate it because its times are still off. So a lot will hinge on the dynamics of the two processes and how they play out in the final answer.
It does seem like one of like you are subject to the initial grouping pretty heavily.
The initial assignment of these words, you mean? Yes, that's correct. So this depends on having these words, and obviously if you change the words, then that can also change what happens. Now, we've done some, I'll show you some results a little bit later that have some, where we're actually doing some quantification. And so we've studied in those cases how much difference the words make, like how many words you use. And it doesn't seem to be very sensitive in the cases we've looked at, but this is pretty early work, so I think there's room to look at this more.
What's really damaging, I think, is when you you have a regular signal, regular event happening, and then you switch labels, and maybe you switch back.
Yeah.
Like it's not really going to be, it's not going to be aware of that.
Right. Well, I guess there it depends on what happens. So if you get enough, if in between the switches there's enough samples, it could still deduce the right sort of structure, but it won't know that this label changed and it should have been X and it should have been 1 and it was 2. It won't know that. But if you think of this more as, this is just a dictionary that marks where things are happening in the video, and this is a process for taking that dictionary and organizing it and saying, of the things that are happening, what's the relationship between them in time? If you think about it that way, I could replace these numbers, and it would, of course, change the meaning of these low-level pieces, but I would still get a grouping that makes sense in terms of the, the higher-level picture of what's happening in the video. So.
What I'm thinking is, maybe you've investigated this, but it seems like at some point you want to then take their causal graph and then redo your segmentation.
Yeah, that's right. So there's a lot of things to do. Let me go forward and show you how this works, a little bit more examples, and then there's lots of things to do, I think, based on this that we could talk about. So this is just showing the grouping here, assigning colors now to these subgraphs, and then re-rendering the points based on those assigned colors, and this is just pointing out that this is now a new kind of segmentation of these points. All right, so let's take a look at what this does on more general videos. I'm just going to play you a bunch of examples here. So these are handshake sequences from the Hollywood Action Database, and the point is that the handshakes are going to be viewed in green, and they're going to contain most of the points. So these are all the visual words on the left that you find in the video clip, and on the right are the causal groups, as I showed you before, and we're rendering the handshake groups in green here. And so the point is that it tends to put these together very nicely and then exclude from that set all the background things that don't matter. This is the same video of my son. You can see it's putting together my son and me in a nice little cluster here, and it's excluding the ball motion, the motion of the outlet here in the background as the camera moves, the motion of the sock down here to a large degree. So it's able to separate all these multiple motions that are taking place in the video and just extract one cluster of our interaction. Likewise over here, the same thing. The cyan cluster contains, for the most part, my son and me and our little hand game here, and excludes a lot of the irrelevant things that are going on. Just to show you a few more. These are more examples of adult-child interactions. And once again, we're doing a good job of getting in the cyan set here most of the interaction and excluding the background processes that don't make any difference as far as this interaction is concerned. We do, actually. Yeah. Well, it's only open for data collection, though, so its hours are very sparse. Let me show you another set of examples here. This is in the spirit of all segmentation work, just showing you a bunch of examples and seeing if you like them, basically. So these are some sports data we've been looking at. So this is now just showing all the causal groups, not all the visual words. And then we just go back and re-render one of the groups that we think is salient, just so you can kind of study it more carefully. So this, again, is all the causal groups. And then a particular one that we think is salient.
One example where the cameraman moves in coordination with the player is really interesting, right? Because you can determine who's the focus.
That's right. That's right. Yeah, I think there's a lot you can do with this along the lines of what you were alluding to, of taking this as a first pass and then going back and re-examining what's going on. We're starting to do that, but we don't have results yet. So this is another example. These are all the causal groups. And then a second to see the one that's just a baby. Okay, so that's the idea. Okay, so now I want to talk about a little bit about why we care about this particular data set of children being flung about by their parents and interacted with in various ways. So, and this actually I think is a much larger point I'd like to make about what I really believe is a fantastic opportunity right now for computer scientists and computer vision researchers in particular to really get involved in the study of behavioral disorders and behavioral conditions in children. So I'm sure you're all familiar with autism. It's become the kind of, in our modern times, it's the behavioral disorder that is getting the most attention. And there are a variety of reasons for it receiving the attention that it does. It's clearly a problem of growing societal importance. It's also very complex and has a lot of very, very poorly understood elements that is currently the subject of a lot of research. The point that I want to make about autism is that it's fundamentally a behavioral disorder. And that's probably true. That's true for this condition across all dimensions. So if you want to know whether a child has autism or not, the only way to definitively diagnose the child is to give them a behavioral examination at the age of 5 or 6. The only way to know whether they're at risk for autism when they're much younger, at the age of 1 or 2, is again to do a kind of behavioral examination. And then once you've decided that a child has this condition, you have to begin interventions which are essentially behavioral therapies. And the only way to measure those therapies and decide whether they're effective or not is to do behavioral observations. So this is a condition that affects a large number of Americans. 1 in 80 boys is the most recent number for autism in the US population. And the only way to understand what's going on with these kids is to look at their behavior.
What are the parents?
It's much higher. It's much higher for military families for some reason. There's all kinds of unusual statistics. Yeah. So, I mean, you can really go have a field day with the statistics here. But the point is that this is a pretty large part of the population. And then, autism is not the only behavioral disorder, and it's not the only one that is of societal importance. And all of these disorders are fundamentally about, measuring and studying behavior. Even in conditions like Down syndrome, for example, where you can genetically test definitively whether the child has the condition, the only way to treat the child's condition and improve their life, essentially their outcomes for their life, is to do behavioral interventions. And the only way to measure whether those are effective or not is to do behavioral observations. So even when genetics can help us do diagnosis, it can't help us assess the efficacy of our actual treatment programs. So there's a huge need right now for better techniques and tools for dealing with behavior, motivated by these conditions, but really I think there's a much longer vision than that. So even if you go beyond behavioral disorders, you can just talk about, behavioral aspects of people's lives, and particularly in children. If you can identify things that are happening at various points in a child's life, you can have an impact on what's going on. But that only happens if you know what's going on, and that means you have some way of measuring it. So really I would argue that there's a crying need for abilities to measure behaviors that are quantitative and are scientific and are systematic and can be implemented effectively across a large population like the US, for example. And what's really the tragedy in that is that right now, the technology that exists to measure behavior is the same technology we had 100 years ago, which is a survey form. So if your child has a problem, you bring the child to a specialist and they sit and they ask you questions. Does your child do this? Did your child ever do that? When did your child do this? And that's a useful source of data. But as you can imagine from the process I described, it's a very coarse aspect of behavior. It's very, it's very subjective. It's based on what the parent thinks. And there's lots of evidence in the case of diseases like autism that parents are not objective reporters of what their children are doing. Okay? So it's the best we have, but it's not nearly good enough to provide the kind of intervention and the kind of treatment we should have for these very important societal problems. And so this is a case where I think it's very clear that computer scientists could have a huge impact, because the technology to measure behavior really exists today to a large degree. We have the ability to capture video and audio. We have the ability to extract useful information from these signals. We have the ability to use wearable sensors to get access to things like heart rate and so on that are also relevant indicators of aspects of behavior. So all of these things could be done, and they could be integrated together with advanced algorithms that are, the bread and butter of places like MSR, and that could be used to derive very interesting sort of fine-grained and longitudinal and in-depth portraits of behavior that just don't exist at all right now. Not even in any form, essentially. So I think this is really an opportunity to have a huge impact, and I hope that people will get excited about this and then think about how we could do it. And I think there's an opportunity to reproduce in the behavioral sciences the kinds of impact that technology has had in the medical sciences, where in the last 100 years it's been absolutely transformational how internal medicine is practiced as the direct result of technology. And I think there's an opportunity now to do that in this other domain. Okay, so we're beginning to do this kind of work at Georgia Tech with other collaborators at other schools. And we're focused on a broad set of things, but I want to talk today about a very specific problem where we've used some techniques in computer vision so you can get a sense for a concrete task we might want to work on. So this is actually a task that was motivated by the needs of researchers in psychology, not so much by the needs of families or children themselves, but this is a kind of nice starting point. So there's a very basic problem in psychology when you're doing research in these areas of getting access to the right kinds of data easily. So there's a famous set of studies I'll show you in a second that are based on essentially capturing little snippets of natural behavior of children and studying that behavior to make hypotheses about what you could diagnose or what you could conclude. And the pipeline looks like this. There's a bunch of video that comes in. You somehow analyze it to find the pieces you care about, shown in orange here, and then you get some kind of a tool and you do some very laborious manual coding of what are the behaviors that are actually taking place within these frames. And so we started thinking about this a year or two ago and decided to tackle the first part of this. How could you essentially take a bunch of video that's unstructured with some knowledge of what you're looking for, and then do essentially a kind of content-based retrieval of finding automatically these orange frames that are the things you want. And so we looked initially at this problem of finding social games as a kind of nice sort of starting point for doing this kind of analysis. And the motivation for this on the autism side is a very famous set of studies that were done by a number of folks over the last 20 years, essentially looking at videos of children in natural settings in their homes. And the way they did this is they solicited birthday party videos. So one-year-old children have their first birthday, and the parents tend to videotape those events. And then you can get a large collection of these birthday party videos, and then because it's a retrospective study, you know the outcomes. So you know of those kids which ones ended up having a disorder of some kind, which ones ended up being neurotypical. And what they did is they then took some trained psychologists and they gave them these videos without the outcomes, of course, and they said, look at this, can you find anything in these videos that makes you suspicious that there's something wrong with this child? And they found that, in fact, with a fairly high efficacy, these psychologists could identify at 1 year of age risk factors in the way the children were behaving that were predictive of developing disorders later on. So this was one of the early studies that established the feasibility of early detection of ASD, which is now a very big public health concern in the U.S. And this was based on, of course, mining through this huge amount of video, mostly consisting of candles being blown out on cakes and things that don't matter, and pulling out the little snippets that actually tell you something about the behavior of interest of these children. And so we thought, let's try to look at something like that, and let's, because this is a hard problem, let's narrow it down and look at these social games in particular. And so I'll just quickly take you through the results we have for dealing with these social games. So social games, I'm sure you know about them. They're fundamentally dyadic between two people, and they're a key part of the child's pre-linguistic development. So the turn-taking patterns that evolve and are practiced in social games later inform the child's turn-taking in speech. So as they learn to speak, they learn how to interact. They're building on skills they developed when they played these social games like patty cake and peekaboo and so on. So this is a very rich set of very interesting natural behavior that's very amenable to computer vision analysis. I think much more exciting than lots of activities we've studied in the past. And I really want to encourage people to start looking at this. There's lots of interesting problems you could frame in analyzing just social games, never mind everything else that's going on. So and we have a nice data set of these games that we're going to release for people that want to look at this with us. And obviously they play a crucial role in early childhood development. All right, so let me just show you what's going on with these games. There are a couple of key properties. The main property is this nice repetitive structure. So the games are played multiple times, and they tend to have stages that are well-defined. So here's an example of a peekaboo game. And you have these stages where, in this case, it's being played with a toy. So the toy is being hidden, and the toy reappears. The child is expecting it to happen, and when it reappears, the child is very happy. So you get this kind of sequence. And this has been done multiple times. So kids will never play these games once, basically, is the bottom line. But in spite of the repetition here, there's also a tremendous amount of variability. So the periods of these different stages, if you will, can vary tremendously. The pose of the child, the way they move, all aspects of this change. But this overall regular structure is still there. So this is a problem of finding regular repetitive structure, but this is not the typical kind of periodic signal analysis that we've seen in vision before in looking at periodic activities, for example. The other things you see are insertion events. So in the middle of this game, another peekaboo game played with the cloth here, the mother decides to turn this cloth around. Or you're playing with your son and you get a cell phone call, you stop for a second, answer the phone. So there's all these things that are happened inserted into the game, and obviously to analyze the game you need to be robust to these kinds of insertions and not be fooled by them. So the basic model we have is this notion that these games consist of quasi-periodic motion patterns where there's this repetitive, almost symbolic level of repetition with lots of variability at the signal level in what's actually taking place. And there's one more property that's very interesting of these games is their tremendous variability in expression or in form. So these are three examples of peekaboo. I think most Westerners with kids would say that these are peekaboo games. And yet the variability in these games is really tremendous. Almost anything can be done. As long as you can hide a face-like object, you can play peekaboo. So there's huge variability in what this game is all about, and yet I think it's instantly recognizable. So it's very interesting to be able to actually, say more about these games and categorize them and so on. Okay, so it's a very challenging class of content to analyze. All right, so the algorithm we have for for doing this identification of these repetitive games is very simple, and I'll just take you through it really quickly. And then I'll show you how it connects back to this causal analysis I showed you earlier. And essentially, we're going to use this causal analysis to get a more refined view of what part of the video to pay attention to, so we can be more robust in analyzing these games. I'll show you the algorithm first without this additional segmentation step, so you can get the basic idea, and then it's very simple to integrate it in. So I'll just get it up here, and we'll just go through it real quickly here. So the basic part of this is what you've seen before, taking a bunch of frames, finding the laptive interest points and the descriptors, clustering them with k-means to get the visual words. And at this point, this is the standard thing we've used for everything that I've described earlier, SVM analysis and so on. And all we do to find these games is we do one more step of clustering. So we take these frames and we take the visual words that occur in each frame and we generate a histogram. So this is a way of generating a kind of representation of the frame in terms of the occurrence of these visual words that are inside it. And then we do one more clustering step to cluster these frames over time. So here's the intuition. If Sangmin and I are playing patty cake, for example, then I'm going to make some motions, and he's going to make some motions. Okay, so then in certain frames, I'm going to move, let's say, like this. I'm going to generate a certain set of visual words from those motion, and then I'm going to get a histogram. And I'm going to do this motion repetitively as we interact. The same distribution is going to occur multiple times. So there'll be some frames that are associated with this pose, for example, that will have the similar histograms because the same actions are being performed in those separate frames. Likewise, on Sangmin's side, when we then do this clustering step, we're going to get a symbol here too, for example, which is the key frame, if you will, for my motion like that. And there's going to be another one, let's say 9, which is the key frame for Sangmin's motion back to me. And so the game we play together is going to be describable in terms of the sequence of labels that have this certain repetitive structure. Okay, so that's the intuition. Now, obviously, one problem here is that if there's other things happening in the background, other motion events producing words, those are going to be added into the histogram, and they're going to confuse this analysis. And then the segmentation stuff I talked about earlier can be used to fix that problem. Okay, so that's the connection between the two pieces, is we take this analysis stage and insert it here, and now we can do this decomposition and this sequence generation for each of these subgraphs independently, and that makes it easier to focus on the important pieces and exclude the other things. Once you've got this symbolic sequence, then you can study it, and what you'll see in many examples is that there are these very nice sort of evocative patterns where there's certain symbols being repeated in regular ways. And you can look at this and say, if I could just find these sub-patterns within this larger collection of symbolic events, I could identify the games. And so we devised an algorithm to do that. And it's, again, very straightforward. You build a suffix tree so you can capture all the possible sub-patterns very efficiently. And then we designed a heuristic scoring function that looks for sub-patterns within this larger sequence that have certain desirable properties, that they're long as possible, that they recur at least 2 times, and so on. Yes, Rick?
I'm not familiar with the suffix tree. Can you just take a minute to explain that?
Sure. So it's a way so you've got a long sequence, and what you want to do is search for all subsequences. Okay? You want to examine all subsequences and score them. Okay? And so this is simply a data structure that lets you efficiently enumerate the subsequences by essentially so you pass through the tree from the root to a leaf, and you're looking at a pattern. And so you can examine the sequence from left to right, and you can build this tree that encodes all possible subpatterns that this sequence has inside it. And once you've got the tree, then you can efficiently score all of the possible subpatterns by examining one data structure rather than going back to the sequence again and again. So it's just a data structure for efficiently encoding all the substrings within a longer string so you can score them effectively.
Okay, so the way to interpret this particular tree is from a 2, you can follow that by a 1?
Let's see. So I'm not sure where this, I'm not sure. I think this 1 should go here probably. I don't know what this 2 is. I think the 2 is probably this node. I guess there's some question about where these numbers go. But I think what this is supposed to suggest.
It's an H, right? So labels with H.
Yeah.
Okay, I was just curious because I'm familiar with all these other data structures like in Markov models or
So I'm not sure for this particular rendering what actually this is my student's figure, and I'm not sure exactly what she meant to encode with these particular values. But the bottom line is that each of these leaves, so the path from the root to a leaf is a subpattern, and you can essentially quickly explore all the subpatterns by operating on this data structure and generate scores. And all we do is we design the scoring function, and then once you've got the scoring function, you can simply evaluate it on this tree, and then you can pick a threshold level, which is essentially how much quasi-periodicity you want before you say that it's a pattern of interest to you, and you can then threshold and score all these subpatterns with this threshold level and pull out the ones that are above threshold as your examples. So that's the way we use it. So we take a sliding window, we do all the analysis I mentioned to you over the sliding window, and then we take all the subpatterns within that sliding window once we have the sequence, and we pull out the ones that are above threshold and call those quasi-periodic patterns. Okay, so then if you look at what that does, these are just 4 keyframes from the video that are associated with different labels in this sequence. And you can see that in this example, this is a pretty favorable example. But in this example, you've got very nice sort of identification of even the stages of the game. So these are different stages of this patty cake game corresponding to these different symbolic labels in the sequence. And it's not always as beautiful as that example, but we do seem to find pretty good capture of the structure in general. And I can show you some evidence for that. So the way this video clip was produced is we take these videos. These are all videos of social games just downloaded from YouTube. So there's no retrieval problem here. We know it's social games. What we want to do is see whether the analysis is going to produce the frames of interest in the right way. So the only way to get a frame rendered into this clip is if the frame is associated with one of these symbols in our sequence. So all the frames that are 2 will get rendered 4, 9, and 6, but anything else won't. So if the pattern mining algorithm misses some frames that are really important, they're not going to be rendered. You won't see them. So if you watch this clip and it looks like a patty cake game, then it means the pattern we've mined is capturing, at least qualitatively, what's important in this content. And the labels here of what's going on were done by my student, not by an algorithm, obviously. So I'll just play these for you so you can see them. So it's, the jumps that you see are when frames are being dropped. So it's not coding everything, of course. But in general, you can recognize pretty well what's going on by simply looking at the coded frames. So this seems to do a pretty good job of capturing the important pieces in this kind of footage. Okay, go forward. Okay, so now I want to show you some retrieval results. So this is an experiment we did at the lab. We have a lab at Georgia Tech where we do child study experiments. And here we went in with our own children and we tried to play with them in ways that would produce social games. We had a list in advance of 4 or 5 social games that we wanted to do with our kids. But you know how it is with kids. They always want to do things you don't expect. And so as you're just kind of in the moment playing with them, you just go with the flow. So we just did this for 85 minutes. And then we had our psychologist collaborators look back over this footage and identify, essentially at the frame level, which frames were social games and which ones were not. And so we came up with a list of 11 types of social games that were being played within this 85 minutes of data. And so the goal then is to do a retrieval experiment. So we're going to take the sliding window I mentioned before, we're going to slide it across the 85 minutes of video. In every evaluation of this window, we're going to enumerate these patterns, and then we're going to compare them to a threshold and decide whether or not there's a social game there. And since we have ground truth, we can determine whether our method was retrieving the social games reliably or not. All right, so first I'll just show you some examples of retrieved behavior. Let me just show you, I think I'll show you these first, actually. So these are just some examples of the basic algorithm working on this footage. Some true positives here. It's kind of a drumming game. And this is a true negative, just picking up some toys, not doing any kind of real interaction here. And this is an interesting false positive. So there's obviously a repetitive motion taking place here. It's not a social game, of course, but since our algorithm is really just looking for these repetitive motions, it gets confused. And this is an example of what was a false negative initially for us, which is we didn't detect this game in part because of the distraction of various other objects in the scene. But now with this new causal analysis, we can get it. So I'll show you that. I'll show you those results now. So this is the similar results, and now just showing the effectiveness of this causal analysis in increasing the reliability of the retrieval process. So the way to interpret this is on the left are all the causal groups. We take the same analysis procedure I described and apply it to every causal group, and on the right is simply which causal groups were marked as being social games in green and which ones were not, marked in red. And so we can now turn this into a true positive, finding the social interaction in spite of all the distracting things in the background. So every green cluster is retrieved by the method as a social game. Okay. These are some more true positive and so on. All right. So this is the basic precision recall curve. This is actually before we did the causal analysis. The main thing I wanted to make about this, main point to make about this is that if a psychologist is using this data for a research project, what they're going to do essentially is randomly sample the video. So their precision recall curve is really this horizontal line. They're going to decide what fraction of the video to look at, and then they're going to get that fraction of the true examples of interest to them as a result. If they sample half the video, then the recall will be 0.5. They'll get half the behaviors of interest when they exhaustively go through and look at those random samples. And then the precision is going to be more or less the same because whatever the random sample is, whatever the fraction of the data is that contains the targets of interest, that's going to be the part that they actually want to find, and they'll look at all the rest as well. So they can essentially move on this horizontal line by deciding how much of the video to sample at random. And all we're saying with this graph is that by having this automatic retrieval system, we can push these curves above this line, which means that for the same level of effort, looking at half the video, we can improve the precision of their search process quite significantly. And all this means is our method is working better than chance, okay, which is not very hard. But if you're going to look at 3 hours of video, a precision of 0.7 versus 0.5 can be a big difference. It can really make your time more effectively spent. And then the causal analysis generally improves things. So this is showing the dotted lines of those curves you saw before, and the solid lines are the ones that come from doing the causal analysis, and it generally raises the level of the performance because it's not confused by background points quite so easily. And I'll just skip over this. Okay, so one more thing we tried. So there's another obvious question about whether you could use this for categorization, not just for retrieval, but for categorization as well. And so the basic challenge in categorization is you've got this ability to do this causal analysis, but you don't know which of these causal sets is actually the important one. So you've got a video that's got some interesting behavior in it, and you've got a model that you've trained with an SVM to recognize that behavior, but you don't know which of the particular causal sets actually is the right one. And so there's a nice piece of machine learning that's kind of well suited for this problem, which is called multiple instance learning, where you essentially have what are known as bags, collections of examples that you don't know their labels, but you know, for example, that the positive bags have at least one positive example in them, and the negative bags don't have any positive examples in them. So with that framework, you can actually do some nice sort of learning in various paradigms, including the SVM paradigm, where you actually design a classifier that can fit a decision boundary to this data organized into bags, and even identify within the bags which examples are the ones that are actually the positive ones. So we applied that machinery essentially to our representation and got some reasonable results. Okay, so so the example would be being able to identify, analyze the data in a bag. So a bag is a collection of two causal sets here. One is the positive example of some social interaction. The other is a negative example of just pretending to eat, basically. And we can get we can separate the two out. So I'll just show you some results of this analysis. This is not published yet, but I'll just show you a video so you can see what's going on. Here it is. So here you'll see, again, these are the different causal sets. The red one is the one we think is salient, but that's just our assessment. And then the label at the bottom is automatically produced by the algorithm. So you can see the ones that it's getting correct. It's getting volleyball correct here, and then you'll see ones that are incorrect. These are the same sports videos you saw earlier. So badminton, volleyball, tennis, table tennis, and a few others. And these are some mistakes.
So you were trying to infer which sport?
Right. Yeah, this is a supervised learning paradigm. So we have training examples of different sports. We gave the system. We trained an SVM classifier using this multiple instance learning machinery. And this is now showing the testing examples. And these are some social games doing the same idea. So there's 3 different kinds of social games here. Toss the baby and tickle the baby and one other one I forgot. And we're just trying to predict which kind of game it is based on the visual representation. So these are all correct examples. You can see that he's tossing the baby, and that's what the system says he's doing. And you'll see some incorrect ones in a second.
Do you hold the baby at the second story window?
No, we don't have that one. there's a lot of games that you could have that we are missing right now. And these are the mistakes. So it's the usual paradigm, when you're talking about segmentation or some process like that. You can often look at it and tell what's going on. And then when you get to the SVM's case, it's really hard to know if it's wrong, why it's wrong. But you can kind of see that tossing and patty cake could be confusable, perhaps. But actually, patty cake seems to be confusable with everything, essentially. But these are pretty preliminary results, I would say. So we still are doing more analysis. Okay, that's probably enough of that. Okay, so in conclusion, so we talked about a concept of quasi-periodic event analysis to do retrieval of social games in video. We proposed a causal analysis method for organizing visual events over time into groups based on their interactions. And we talked about how this could be used to find social interactions of various kinds in fairly challenging real-world videos. I want to make essentially 2 points looking forward. One point is that I think there's a lot of room to look at the temporal dimension of video. And I think this is an area that's really underexplored in vision and is ripe for more work. So I'd encourage people to do that. And we have a number of data sets that we're going to release of all the things that you've seen today that you can take a look at and try to improve on our methods and see and pose and answer other questions, very interesting questions about how things are going in time. And I also want to come back and emphasize again that I think there's a great potential right now for computer scientists in general, for computer vision researchers to have a positive impact in the study of behavior. And this is a case where there's great science to be done on the computer science side and great opportunities for societal impact in terms of behavioral sciences and behavioral disorders. So if you're interested in that, I'd love to talk to you more about that. We're really trying to get some activities going in this area at Georgia Tech and more broadly as well. Okay, thanks.
Any other questions for our speaker?
Have you been following Dev Roy's work?
A little bit, yeah.
What's his tool?
I don't actually know the answer to that question. What I know about is this experiment where he videotaped his kid for a year or something like that.
Like 3 years.
3 years, okay.
I think. But yeah, so and he has. I mean, his pitch is kind of similar in the sense that he's looking for these pulling things out of these vast longitudinal studies that we haven't really been able.
That's right. Yeah, I guess one thing I would say there is that I think the study of behavior is really a rich and interesting area, but it's like any other discipline where if you have a set of well-defined questions, I think it really helps to advance the frontier of science. So I would say that the benefit that I see for this technology is really not computer scientists randomly videotaping things and then posing questions, but really working closely with psychologists and people that study children's behavior. And there are a lot of questions in that domain that people have already thought about for decades and centuries even that don't have any kind of quantitative empirical answer because the data collection technology was never there. So if I was going to work in this area, my approach would be to really look at what are the questions of interest and then really try to frame them in a kind of careful way. So what we're doing, for example, is there's a screening instrument that's been developed by some of our collaborators that's actually trying to do early detection of autism based on behavioral observation. And that screening instrument has a number of very well-defined behavioral measurement challenges built into it, and we're just trying to address those challenges sort of systematically one by one. So the goal would be to really, measure something very precise, and then because it's a screening instrument, it's being validated independently, and there's a good story for why everything that's in there is in there. So you really can build your analysis framework on a kind of solid scientific foundation in terms of drawing from the literature on psychology and on autism. So that's kind of the way I would approach it if I was, to work in this area. Yeah, John.
I wonder if it would be easy to use your framework to graft on another sensor that's not a camera. Like
very much so.
Or an accelerometer.
Yeah, I think that's really interesting. We haven't done anything like that yet. I think I think this machinery that I'm talking about could be really useful in that domain and also in the audio domain. I think there's a ton of things you could do with it, and we just haven't had time to do them yet. But and actually, in the accelerometer case, we don't really have data yet that we would use for that purpose. But I think it's a great idea. Yeah, I think we can definitely do something. Rich?
There are other information streams that yield things that are like videos. So I'm thinking about fMRI while
Right.
the person reads and
That's
talks
right.
and things like that. Have you thought about applying any of this analysis?
Yeah, what's interesting actually is
Causal
that
structure in the brain?
yeah, what's interesting is that those guys are actually way ahead of us in that regard. So these kind of Granger causal analysis techniques and so on, they've been used in those disciplines in EEG analysis and in analyzing neural spike data, analyzing brain data. It's actually been done for decades. So that community was an early adopter of these techniques and have used them a lot. And it's really in vision we're kind of catching up in some sense to using some of those tools. Now I think there is a difference between, in the case of analyzing the brain in particular, like the kind of data sets you talked about, you can say a lot about what you're looking at, and then you have reason to believe certain things might exist or not exist. Obviously in video, it's a little different story. It's more like an exploratory data analysis. You don't really know what visual words you expect to find. You don't really know necessarily what patterns of interaction you're going to get. So it's a little bit more of a, as is often the case in vision, it's a little more of a tool for exploring these relations. We don't have great a priori models for what we expect to happen. So I think it may play a different role in our community, but definitely we can look to those guys for. And in fact, there's some more advanced, or at least more advanced, but different versions of this that are being used in that community. We can look at to try other versions of this algorithm. So there's definitely a lot of connections there. Yeah.
One thing that's interesting about the example that you've been working with is they do tend to have a very particular kind of spatial structure.
That's right.
Even though you're for the most part eliminating that.
That's right.
Like you have this, they're almost the actions that each person takes in these dyadic interactions are basically mirrors of each other.
That's right.
And that could be an interesting source of information. I mean, granted, you look very different than your son.
That's right.
And that's a problem, but there is sort of a push and pull that you can almost pull out of, if you look at qualities of motion, just adds just a little bit of spatial.
Yeah, no, I totally agree with you, and I think that, one way to look at this is that these visual words and their organization give you kind of landmarks, if you will, into the video, where at particular frames, at particular locations, you know something now about what's happening. So then you can think about going back and leveraging that knowledge to then do more analysis, and do spatial clustering and things like that would, expose the broader picture. So I'm very interested in that. We haven't done it yet, but.
Feature to give you information like I've seen this frame here looks an awful lot like a frame that I saw.
Yeah, well, clustering is just putting together the words whose signatures are similar in terms of a Euclidean or a histogram intersection kernel distance in your feature space. So they are making statements about correspondence essentially based on appearance at the level of the features you're measuring. So it definitely is doing that. Now I think the question is how to kind of make that more precise in some sense. If you really wanted to drill down deeper, you'd have to say more than what these correspondences are giving you. But I think there may be ways to do that. Yeah, that's a good question.
Well, let's thanks, Jim,
Thanks.
once more.